You're going to learn about the lake, what lakes are about, and then how they work. So it takes a while to go through that. And if you have a question, just shout it out while I'm going, because otherwise I'm a bulldozer. And really what I want to do, my goal here is to get the principles of lakes in front of you so that you see that it's not a simple, straightforward thing. And when you hear simple answers, it doesn't necessarily work very well. And this lake is particularly interesting. And so what we have is a commons. It's a commons, and it's the county commons. Just like every commons is a commons, everybody would use the commons thinking that it's a unique entity unto itself. As you will see, lakes are not, because it's everything that's upslope is going to then affect the lake. And I'm going to turn you off. Let's see if this works. I got new tech stuff. All right. So the people that are interested in the lake is all of us, and certainly the tourist industry is as well. And even though they would have their own pool, people come here for the lake, to come to fish, to come to do all those things, even if they don't swim in it. And of course, we have all of the other folks around the lake that live here, some for thousands of years. That lake is very, very important, and it's of course changed. One thing is to understand how significant lakes are in the world. If you look at the entire world population of oceans, amount of ocean, total global water, and you just make that 100%, the top 2.5% is fresh water. That's not very much fresh water. If you take that fresh water and see how it distributes, you got glaciers and ice caps, groundwater, and surface and other fresh water is only 1.2% of that 2.5%. So that's even less. And then you take that whole thing and you break it down, and you will see that lakes are 20% of the 1.2%, which is of 2.5%. It works out to 6/1000ths of a percent of the world's water. It gets better than that. The lakes break down into different types. There's about 25 different types, 23 to 25 different types, depends how much of a splitter you are, right? And so we have volcanic lakes, oxbow lakes, glacial lakes, tectonic lakes, which is what we are, which we described during our class on that. And then we have oases and artificial lakes, which are the dams. And of course, here is a lake formed from glaciers. As we looked at our polar vortex anomaly that sat there for several thousand years and developed glaciers that were a couple of miles deep. And when they scraped out these rivers that basically ran through there, they formed lakes. And so that's how the Great Lakes were formed. And so after all of the melting that happened with the glaciers, you have lakes that are only 10,000 years old. So these are relatively young lakes. Ours is 400, 500,000 years old, maybe, depending. If you talk to a geologist, 1 million, maybe more. If you talk to people who actually have empirical evidence, you're talking 500,000 years. There, you're only talking 10,000 years. Now, Scott Dam is an example of an impoundment, and so it's uniquely situated as a headwaters. If you wait for the Record B coming out pretty soon, we'll have an article on Scott Dam and its significance for the Eel River. If you want to read it early, it's already on the Bloom, the Lake County Bloom in Middletown. And so anyway, that's Scott Dam. That's an impoundment, and this is an oxbow lake. So this is a big meander, and every time that it gets enough water, it'll break off and isolate a oxbow. You can see one isolated there, one's isolated there. It'll form another meander after that. Every time it gets floodwaters, forms other meanders. Sacramento Delta used to be full of oxbows. You can't see them anymore. The only way I knew that there was so many was looking at it under satellite interpretation. They had interpreted, used different wavelengths. So that was the only way I knew there were so many, but it was forming through the entire Sacramento Valley. Volcanic lakes, of course, as you know, they get kind of sealed off and then it holds water, crater lake. So, other types of lakes. Those that have different levels of nutrients. So here's a lake that has very, very nutrient poor, lower levels of nutrients. It's called oligotrophic, basically without trophic. So it's very, very low in nutrients. And one example would be Lake Tahoe, which believes that they're an oligotrophic lake. And so what you will see is the limnetic zone is usually very, very low, so that the light passes very down. So it's usually very deep limnetic zone. This shows a large profundal zone, but that's where the light doesn't reach, but actually they can get pretty low. You don't see very much littoral zone in a oligotrophic lake, or you can see no zone around the edge. Now, one thing that happens on these lakes is you get a layer of cold water and a layer of warm water, so it's a two-story lake. You ever swim in a lake and you can feel that cold water down there? So, all right. So basically what will happen is it'll get so warm at the top and so cold at the bottom that the wind will not mix it anymore. The two won't mix. But then in the autumn, once the top layer loses that heat and the two temperatures get to be the same, then it starts to overturn. In fact, it can get colder on the surface than it will lower, and it can just roll right over, just like that, called a lake overturn. So this is pretty common in deep lakes. And Tahoe gets very, very clear along the edge. You can see no vegetation or anything in that. A mesotrophic lake is one where it's kind of in the middle between the nutrients. Most of the lakes are like this. And usually that's in a forested surrounding, but it doesn't have to be. There's some algae in Lake Summer. There's a lot of deciduous trees usually around, and those come in and provide the nitrogen for the lake. Shallow plants along the edge, and a slight sediment buildup, and it does in fact have a thermocline just like the other lakes. So if they're deep enough, they have a thermocline, and they can have that same lake turnover kind of thing. Every time you have the lake turnover, all the nutrients that are on the bottom will then roll to the top. So the next year, because of that rollover, then you get a nice bloom in the spring. And so these thermocline lakes that roll over, those are kind of dramatic in the spring. But yet there's not much nutrient because it's right in the middle. Now this is a lake that is a mesotrophic lake, but it's high altitude, but it's kind of out of control because somewhere there's nutrients coming in, so it doesn't have to look like the forest environment. Lake Tahoe is moving towards a mesotrophic lake because they have so much sediment coming in. In fact, they can't seem to get it stopped, but in any case, that can also happen. So here we have a eutrophic, nutrient-rich lake. This is on the top end of the scale. And these very old eutrophic warm water ecosystems are rare. And the reason is they silt in and they form valley floors. And so all the valley floors around here, Sacramento Valley, you drive around, if it's a valley, it used to be a wetland. It used to be a lake. It used to be something that was moist at some time in the past. The Sacramento Valley used to be very wet. In fact, at the other end of it, found fossils up there. So you have a very unique situation with so little water that is fresh. This is the rarest of fresh water. It's a very old warm water eutrophic ecosystem. We're probably the only one that is as old as we are in the world. I can't find another one. I've been looking for quite a while. There's got to be one somewhere, right? 500,000 years old? I'm just using that number. I can't find one. So if that's the case, we're extremely unique. And of course, you're going to have very dense fish populations. You're going to have high concentrations of nutrient and plankton in that area. You're going to have a very wide littoral zone. Now, littoral zone is the zone that's closest to the shoreline. You're going to have a sandy or clay bottom. And in our case, it's going to be silty bottom. It can be clear up to your neck if you're not careful. And the sun will not penetrate very far. Natural eutrophication on one of those lakes, if they start out really deep, will take a long time. And so you can have a time of centuries before it fills in. Ours doesn't fill in simply because it is tectonic in nature, and so the bottom keeps dropping down, and we get a little more room for more sediment over time. About a 1/4 inch to a 1/2 inch every year. 1/4 inch, I'd say, be more reasonable in saying, and then about that much in sediment. However, we're actually getting more sediment at a speed higher than the natural rate of drop has been in the past. In 1960, DWR did a survey to see if the rate of input was higher than the rate of sink, and they said that instead of 500,000 years for this never filling in, it will fill in at about 5,000 years at the rate that it's filling in now. which is normal rate. That's about what a valley usually fills in, 5,000, 10,000 years. However, if you have one where the rate is controlled, it's a very large area, it can be centuries longer. So it can be up to 100,000 years. Ours in 5,000 years, so that was the rate at one time, 1960. I still have the paper, so I can back that up. In the littoral zone, that zone that's right on the edge, you have emergent vegetation, you have floating leaf plants, and then you have submerged plants, you have a lot of algae. If the algae is so thick that the sunlight won't get down, then this won't grow. So as you go down in depth, you have more algae, you'll have less submerged plants. They will disappear at some level where the sunlight will get in and allow them to grow off the bottom. And so we have the emergent vegetation, the vegetation that comes and grows out of that real near shoreline. And people look at that and they say, well, that's the filtration mechanism for the lake. It actually is not. It is taking nutrients up for sure, and I will tell you that it's got a lot more little fish in there than you can shake a stick at, a lot of phytoplankton, a lot of things going on. Where that's important is in the wetlands where the streams come in. That's where it actually causes the silt to drop out. But along the shoreline, it is there for the fish. It's there that makes the entire system works, and it's taking up those nutrients. Take up those nutrients, it's not going to be in a water column, not going to have as much phytoplankton, not going to have as much cyanobacteria. A lot of other things won't happen as much if you were to have more vegetation that's actually growing within the system. So if it grows in the system, it's not out there for the phytoplankton. If you don't have it, phytoplankton have more of it. And then you have less sunlight, doesn't grow on the bottom. All of those things are kind of a balancing act. And Clear Lake, if you were to look at the bathymetry, this end of it, the large end, is shallower than these two arms. Now the two arms are the youngest part of the lake, and yet they're deeper. And so when the whole lake started keep sinking, finally these parts here started to sink with it. They were sinking anyway because they had big fault lines. But those fault lines started to sink with it until they got to be a wetland, then they got to be a lake, and now they're part of the lake and even deeper. And so they actually can age that to say that between 10 and 20,000 years ago, it was not part of the lake system. So if you give it the longest period of time of 20,000 years, then you do not have 20,000 years worth of sediment buildup, like that one does up here. 20,000 on top, that is not a deep. Both of them are still sinking at that same rate, but you don't have the depth up there that you have down here. Tells me that maybe we don't get as much siltation down here as we do at the upper end. So keep that in the back of your mind for later. So eutrophication, you get increased nitrogen and phosphate. Nitrogen and phosphate are one of the 6 elements that I told you that 98% of all living creature, all biomass has. So that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And so those two, phosphorus and sulfur, or nitrogen and sulfur, are the two that are limiting factors for a lot of life forms. So if you have low nitrogen and low sulfur, you will have a oligotrophic lake. So if you have high phosphorus or high nitrogen, depending on which one or both, then you'll have a eutrophic lake. Depending on which one or both is very, very important, because if you have a lot of nitrogen like we do, and you have a lot of phosphorus like we do, you're going to have a lot of everything, because nothing's limited. And that's exactly why everything happens in this lake, making it a very complex ecosystem. Now, the other thing you need to know is that if you have a lot of life forms that are in this water column, they're respiring, they're using up oxygen. Just like if this room were just jam-packed full of people and everybody started getting sleepy, you're losing oxygen because you have a lot of biological oxidation demand. You're using oxygen. So BO2, you're producing O2 because you have the phytoplanktons, everything that produces oxygen is in this water column, but you also have BOD because everything respires. All of the fish, all the living forms, including the plants and animals, they're producing more oxygen than they're taking in order to respire. So at night, what happens? When the sun goes down, they're only respiring higher biological oxidation demand. Now keep in mind, while this is going on, that you got a one-way system. You have primary producers, that's the ones that produce the oxygen. Then everybody else is a consumer all the way up. And at each level you lose, it's only 10% of the energy form taken from the one that's in front of it. So this produces 100% of the energy that you can have. The primary consumers only get 10% of that. 10% of that goes into the secondary, 10% of that goes into the third, and 10% of that goes into the apex predators, which the eagles and all of that sort of thing. And in between, you're losing all of it off to heat. So it's not a very efficient system. But it is even less efficient if it were not based on oxygen. So keep that in mind. At one time, life forms were not based on oxygen. And then when they did become based on oxygen, when they could use oxygen as their life form or their process, they became less necessary to produce or to retain as much of the sun's energy. And so therefore, they can get by with less of the energy and actually still able to mobilize and all the other things. All of these will go into decomposition. All of that decomposition, everything else is left, all goes to heat, and you recycle nutrients. Here's the key thing. You can recycle nutrients. You cannot recycle the sun's energy. It's a one-way street. When it starts down here, it chugs right on through until it's lost and out in the atmosphere and gone. And so that's just the way it works.
Now, does that say energy lost as heat? We can't read it. I think that's
sorry, energy lost as heat. Now here's another factoid. Fish need, I'm going to put up there 8 to 10 milligrams per liter of oxygen in the water, dissolved oxygen in the water. Some can live a little bit lower, some can get down to 4, some get even lower than that. But I'll tell you what, 8 to 10 is, that's pretty nice. And there's some water columns where you can get super saturated and have 12, 13 milligrams per liter, parts per million. But 8 to 10, we'll use that as an example. If I took that 8 to 10 milligrams per liter and I say, all right, in the atmosphere we have 21%. This is what we need, 21%. And turn that into the same units, that's the same as saying it's 210,000 milligrams per liter. That's how much oxygen you need compared to a fish. That's why you're not breathing water. You can't use it. And so the other thing is that if you get a lot of nutrients in the water column and you get a lot of algae, everybody's happy camper during the daytime, at nighttime, or in fact, if you get so much algae that the bottom plants die off, then once they die off, they will start to decompose, they'll use up oxygen. Anytime that the sunlight doesn't reach the bottom or reach it up here, the same thing can happen. And then of course at night, the fish will start to use up oxygen, everything will. You're going to wind up with the water deoxygenated and you get a fish kill. And so we can get some pretty good fish kills simply because everything is so loaded with nutrients. And so at night, everything drops down. I've investigated, one job I had, they sent me all over the state looking at fish kills. Okay, Jim, go down there and investigate this thing. We take all kinds of samples. But 99% of the time, this is what it was we just had too much stuff growing in there, too much fertilizer. It was running off people's lawns, it was running off golf courses, and they would call fishing a game, off I went. And I went down to Southern California, I don't know how many times, you gotta get the fertilizer out of, So in any case, this can happen to us. Now here's where we bring the other concept in. Cyanobacteria came about very early in our lifetime. So if you go back billions of years, the Earth was formed right here, 5 billion years ago. And then the prokaryotes came along. These were the earliest form of bacteria. So these are the earliest form of bacteria, and they would operate in an anaerobic or no oxygen condition. And so they would be moving around, and all of a sudden they learned how to develop photosynthesis. They were then cyanobacteria. They developed photosynthesis, and they were moving around using this resource, and they were giving off oxygen. Oxygen started to build up in the atmosphere, and oxygen building up in the atmosphere dampens down those cyanobacteria because it's poison to them. They're giving it off as a waste product, and they get too much of it, and so that's toxic to them. But the bacteria, the protozoa, and everything else started using that oxygen in the atmosphere, and it's a much more efficient way to use energy, and all of a sudden you have this explosion of life after oxygen came about. Cyanobacteria is still better off without oxygen. Everything else is better off with oxygen. We can breathe 100% oxygen. It doesn't bother us. But cyanobacteria will dominate from biological oxidation demand, a drop in oxygen in the water column. It will dominate because of nitrogen and phosphorus nutrients, not directly, but indirectly because they're fueling everything else, causing this extreme drop. And so once you get so that you have a crash in that oxygen, for any reason, then all of a sudden cyanobacteria can use these nutrients and then they take off. And of course, they love nitrogen and phosphorus. They have what's called a luxury uptake. They will suck up phosphorus and then will keep it for several life changes, with several divisions, until they finally run out of it, and then they'll die and the next cell will come along and take over. The other thing is, where is all this stuff coming from? It's really got to look at it from the standpoint that we don't get a lot of this except from a couple of sources. So nitrogen compounds are produced by cars, from untreated sewage. Our sewage is in a pipe that goes somewhere else. For the most part, we still get a little. And discharge of, internal combustion engines, furnaces, runoff and erosion from cultivation, runoff from streets, lawns, construction lots, all nitrogen phosphates, manure runoffs from feedlots, nitrogen phosphate from those, or our natural system up here has a lot of critters. We have a lot of cattle. Natural runoff from nitrates and phosphates, and runoff from erosion, cultivation, mining, construction, and poor land use. Those are the two that produce more of the nitrogen and phosphates for this lake than anything else. And of course, we get some heavy metals. We did a satellite interpretation of the landform where they looked at it from spectrograph, and so that from the reflected sunlight, and they could look through this spectrograph, and they said, this looks like a very heavy phosphorus-rich area. We didn't get a chance to do the ground truthing on this, and it only, you can see kind of a false line. It was supposed to mirror the image of the county of Lake, so they didn't do this. They just kind of isolated it to here. And so that's our county, and it has a lot of phosphate in the soil. How much does it have, you ask? It has 10 times the national average. So we get about 0.8%. And it's fairly poor in most places, so they have to add phosphorus to the soils to boost them, whereas Lake County, because all of its volcanics, has a high amount of phosphorus available in the soil. And so that's a good thing. And because we have so much, a lot of the plants that we have don't need as much. There's a lot of symbiotic relationships we could talk about, but we have a lot of phosphorus. So it's not limiting. Now, in some areas, you can get, this I like to call this hippopotamus eutrophic, because you can get so much plant growth that on the surface in a shallow area, it looks like a hippopotamus would be happy there. And we have a little bit of this here over in Anderson Marsh, and we would love to have a lot more, because that's where a lot of this stuff can be processed and sink out before it gets into the lake. That's the advantage of having these wetlands. As the water comes through and goes into the lake, a lot of that gets locked up in the plant material. A lot of it will then, as it dies, it'll get locked up in the soil bottom. New plants the next year, new phosphorus, all of it gets locked up in the soil. So that's exactly where we'd like to have our phosphorus and nitrogen excesses. Now, they have a hippopotamus machine in some places in the world. This is down in Florida. And this is hydrilla, and of course they've got a lot of hydrilla. It just takes off like a weed. We have it in the lake here, but they try to keep it controlled. So you'll never see it, but they see a lot of it, so they chew it up. We had machines that used to do the cutting here in the lake, because that was all good. You could pull the weeds out of the lake, and you could take it and dump it into a truck and haul it off. But unfortunately, when it did that cutting, if there was any hydrilla, the hydrilla that grows from the nodes. So every node, so if you were to break it up, every node that got broken up and left behind would grow new hydrilla. So it's a little like the starfish, in the ocean, same thing. So in any case, they said, nah, you're going to have to put herbicides down anyway. And so that's why they only use herbicides. They don't use this method because it's too expensive if you have to add herbicides on top of it. There's another way to do it. Ask me about that sometime. I'm still angry about it. But in any case, I digress. Here's the thing that you need to know. We have lots of birds because we have a lot of these niche habitats, such as what we just covered in our habitat class or ecology class. So we have lots of these niches, and we're going to have lots of birds, we're going to have lots of animals, we're going to have lots of wildlife, using up all that nitrogen nutrients, because we have so much nutrients, we're going to have lots of critters, and that's the good thing. So all of this business of people not liking the situation, it doesn't carry over very well unless you're a fish that dies from lack of oxygen. It's actually a good lake, but it's bad from the people's standpoint. And so yes, you can regulate it. You just have to understand what's out of whack. But everything else likes it. We have a warm lake. If you've seen it at night, this is a night picture. I'm just kidding. So, a warm lake will speed things up. You get a higher biological oxidation demand because everything's working harder. You also get less capability for oxygen to be in the water column. So water has less oxygen. You have more energy, less oxygen, and that's a bad deal from the standpoint of BOD. I'm still angry about it. But in any case, I digress. Here's the thing that you need to know. We have lots of birds because we have a lot of these niche habitats, such as what we just covered in our habitat class or ecology class. So we have lots of these niches, and we're going to have lots of birds, we're going to have lots of animals, we're going to have lots of wildlife, using up all that nitrogen nutrients, because we have so much nutrients, we're going to have lots of critters, and that's the good thing. So all of this business of people not liking the situation, it doesn't carry over very well unless you're a fish that dies from lack of oxygen. It's actually a good lake, but it's bad from the people's standpoint. And so yes, you can regulate it. You just have to understand what's out of whack. But everything else likes it. We have a warm lake. If you've seen it at night, this is a night picture. I'm just kidding. So, a warm lake will speed things up. You get a higher biological oxidation demand because everything's working harder. You also get less capability for oxygen to be in the water column. So water has less oxygen. You have more energy, less oxygen, and that's a bad deal from the standpoint of BOD.
What are we looking at?
That is just a photo and interpretation of change. You know, I doctored it. I admit it, I doctored
Looks
it.
like it's flame.
Yeah, it is flame. I added flame to it. I wanted to make it look Okay, well anyway, a warm lake, I'm just trying to, okay, never mind. Okay, but here's real data. Okay, this is real data. 1969 through the years to 2001, every blue is a winter, every other color is during the summer. So this is a graph of every year of all of them, all of the measurements taken together and then averaged out. And then they put all of it onto one graph so you could see it from 69 to 2002. So what you see is during the summer, in the water column, it gets warm almost all the way down. Right there, it gets all the way down to the bottom. So it can get pretty warm in the summertime. In fact, you can, if you look at the degrees over here, those are in centigrade, so it can get up to 80s, 85, and it'll get down to the 40s and 50s, but usually the 50s, 45, 50. 45 is very rare, so that's a really, really cool time right there. And so we actually had some really cool period right in here, and the threadfin shad, which are introduced, and they are normally found down on the Gulf Coast. They put them in these lakes. Fishermen like to bring them up, put them in the lakes because we don't know what we're doing. So they put them in the lakes for us so they'll feed the bass. And the bass populations take off. But other things happen that they don't think about. Now, it just happened in the 90s. In fact, 1990, right here, when it really got cold, through here, we also had a drought. All of the threadfin shad disappeared, and I got a graph showing what happened. Okay, so here we have another principle. That is, with all of this that's going on in the lake and all of the die-off and all of the other business, the benthic area starts to get very anaerobic because it has so much nutrient value in the benthic area. And so all that sediment that comes in with all of everything else that's going on, it will actually change, and the warm water and all that, it will actually change the composition such that it will give off phosphorus. So phosphorus becomes loosely associated with the soil. It becomes associated more with the water column and other chemicals that are in the water column, so phosphorus is released in the water column. And we also have a nitrogen cycle that goes on. I'm not going to do all the cycles because it would take too long, but it comes up into the water column and is available. So any of this sediment that comes in, the reason we're not living in a jungle is because the phosphorus is locked up with the sediment. But when it gets into the lake, people are saying, well, phosphorus is locked up with the sediment, won't create a problem. And then he discovered that no, it does come up out of that sediment because of anaerobic conditions, lack of oxygen, and the high temperatures of the lake. It comes right up into the water column. Now, with phosphorus available, nitrogen available, and the sunlight available, then you're going to get a lot of weeds off the bottom. If you don't get the sunlight all the way down to the bottom, then you won't get weeds growing. So what's happening is we're getting weeds growing, and for the longest period, up until about 1990, people were saying we didn't have any weeds. Starts 1990, all of a sudden we got all these weeds. What the heck is all that about? Now, I call these weeds because I've given in to that, but these are actually are submergent vegetation, and it's all very natural except for the ones that have been introduced. So this is a natural consequence of this kind of lake where these grow up off the bottom, so this is kind of a good thing. So why did they start to grow? Well, it got clearer. And these are psyche depth changes. The psyche depth, the only reason I put the technical term in is because you might hear that term, psyche depth. So there's a guy named Psyche invented this. But basically, yeah. Okay, so it's just a disc. It's white on one side, black on the other. It's on a rope. Drop it down until it disappears, and that's the depth at which it disappears. If you were to drop it down in 1970, it only went 3 feet before it disappeared. And this is the winter conditions, April to October. This is not July and August. So this is when you don't get the big blooms. Why don't you get the big blooms? It's because the sunlight comes in at an angle and bounces off the surface of the water. And if you're a diver, you really know that. It actually gets darker underwater before the sun goes down. You come up, hey, it's the light, what's the deal? Well, the sunlight actually bounces off the bottom. So when the sunlight gets high enough during the summer, and you get the July conditions, it is really right up at the top. June is when it's the highest. It'll go straight down and penetrate the water column. But any other time, you get 3 feet, 1980, 3.2 feet, 1990, 4.5 feet. All of a sudden, it exploded, and now you get 9 feet in some areas. And so the deeper contour lines, you got that submergent vegetation growing up because the sunlight, during those periods of time, up through October, and April particularly, they'll grow right up off the bottom. Now in July and August, throughout the entire year, and everything that's been sampled, it remains constant between 3 and 4 feet, and sometimes 1 foot measurement. In other words, if you were to stuck your hand in like that, you couldn't see your fingers. So it is gone. And that is during all the time during the July and August. Well, what would happen to those plants if all of a sudden the sunlight was shut off? They would die, they would drop to the bottom, BOD. Now, why is it that it doesn't happen every year to get the big fish die off? It's because during April, you get the sunlight on the bottom and they grow up pretty fast because of all the nutrients. And as the light doesn't penetrate as much, it goes from 7 feet to 6 feet to 5 feet, it's growing. 4 feet to 3 feet to 2 feet, it's growing, it's staying ahead of it. And so that's why you see it all summer long. It stays ahead of that growth. How do you get rid of those weeds? If you wanted to, you just start that growth of phytoplankton in April, and you wouldn't see your weeds. And I did a little experiment down here. I threw iron compounds in the water column just to see how it would work. And man, I got a big bloom of phytoplankton. Didn't have any weeds in that area at all. So you can actually manipulate your lake, and you can get rid of the weeds, and you don't have to have all the other business going on. But there's a better way to do it. Just live with the weeds. And if you want to have pathways for boats to get in and out, you can put down weed nets on the bottom. You want as much emergent vegetation as possible in other places because the fishermen love it. You're going to have fish there, and you're going to be able to use up those nutrients in a natural way. Now here's what happened. Threadfin shad were eating all of the zooplankton. And when they ate the zooplankton, then the phytoplankton, which the zooplankton used to eat, took off because there was nobody eating on them. And of course, then you got water transparency went down. And so after 90, the threadfin shad disappeared. The zooplankton, I'm going to show you a picture in a minute, the zooplankton, little guys, then ate all of the phytoplankton, so the water column cleared up. Had nothing to do with entering new or less nutrients into the water column. That all remained the same. It was just the dynamic of the loss of the threadfin shad. But everybody was saying, hey, we're doing a good job. You guys are doing great because there's less nutrients coming into the water column. And when the study was done, that wasn't the case. And in fact, there's graphs you can show of, here's Glotrichia up here, that's the orange one. I'm sorry, green. And then other ones that from different years, you can see that the columns go up and down. There's dominance by different things. There's zooplankton down here. There's dominance at different times of the year. So all of this by plankton toe, they can figure out where these dominants are. Here's some zooplankton, very, very small. You look at it under a scope. This is, I think, 20 power. It may be 50 power. This may be 50 power. So they're very, very small. They eat the phytoplankton. The phytoplankton, these are all cyanobacteria. Phytoplankton are also just as small. They eat some cyanobacteria, not as much as the other phytoplankton, but these are the guys that cause the stink. This one right here is Lingbia. That's the one that you're going to see, the floating that makes the stink, because it has mercaptan that comes off of it, which is a sulfur compound. It loves luxury uptake of sulfur. When it dies, it gives off a beautiful stink. And then this is our Glotrichia right here. That's the one that's really pretty in the water column. Most people just think about where to fish, and there's lots of fish in this lake. That's all they think about. But in fact, we have all these other things going on. This is the Sulphur Bank mine. Of course, that is famous for being a cleanup site. Well, what did it actually produce that creates a toxic site to be cleaned up? Mercury, right? So that's what it's known for. Guess what else? Sulphur Bank mine. What are the 6 elements? Sulfur is one of them. And so it is another limiting element that is not in Clear Lake because we have so much sulfur coming out of the Sulphur Bank mine. It is everywhere. So again, it's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And so now we have a toxicant in the system, but we also have plenty of sulfur. Why is it that they're not cleaning it up? Because here's a couple of thousand points right there for a reason why. All of these sites right up here where there's a lot of population, these are toxic sites for CERCLA, the pollution cleanup program. Those people make a lot of noise. They're right around Washington, D.C., and so there's a lot of work being done there compared to anywhere else. And you can actually look on your calendar of work, and you can see that it radiates from there going out. In any case, we are right there. So this mercury that's in the water column has to methylate in order to biomagnify. Methylation means that instead of being a non-organic, it's a mineral mercury, straight mineral mercury. It has to become an organic mercury before it can be taken up and into the system. Well, that happens in the sediments. So some bacteria will actually take it up and then incorporate it within their system, and then of course all through the food web they start to get picked up because it's been methylated. And there's lots of words, there's a whole class that can be taught on this. Bioaccumulation is the actual uptake. Bioamplification is because some organisms take it up better than others because of their differential feeding. And then biomagnification has to do with the organisms picking it up, going up through the system. So this is the transformation of methylated form to bioaccumulate and biomagnify. It's all done down here in the sediment. And so then there's this big process by where you get the methylated mercury and it gets taken up in the fish, and you can actually get a reduction out of that demethylization back into a system where it goes off as mercury into the atmosphere, and that's why it's everywhere. And so you get 2 mercuries together, it can go off as a gas, and it's all over the United States now because it's in the atmosphere and gets spread around pretty easily. That's all from coal and a lot of other things like it in mining. Mercury plus sulfur can increase methylation, and guess what we have a lot of? Sulfur. and all around that mine. And so there's a lot of methylation that's faster than what they're expecting. This is something that I was kind of waiting to see the science on, and now there's plenty of it. You can find it everywhere. But in any case, that's what happens. And you get methylation. It doesn't have to have mercury, sulfur, but you can. And then, of course, you can have demethylation through the fish decaying and coming back into the system. Now, here's the other principle that we want to put in play, and that is...
Demethylization, how that happens, and how a fish could have a mercury uptake and yet suddenly it loses its...
Then they don't lose it. They die. They go back into the system. And then if the mercury attaches to something that likes better than sulfur, and there's plenty of heavy metals that are out there, then it'll stay in the system. If it actually they die and they're right at the surface layer and there's so much of it that it goes off as a gas, that gas will go all the way to the surface and then get up into the atmosphere. And so usually though, it gets incorporated again in a rich system. It's in a system that's not as rich as ours. You don't get as much gas. It gets incorporated to where it can't come off. Although there's been some research that shows that it's all over the land around here. Not to excess, but it's all over the place, and it's because of that gas. Everywhere that they used it for gold mining, mercury to amalgamate and have it float off, it's everywhere. Because they used to use it in these retort ovens. But in any case, this is the other principle I want to throw at you, and this is our chironomid. This is what they call it, the Lake County midge. And so the Lake County midge is basically a little guy that looks like a mosquito, but they don't bite, and they swarm and make a noise, and they're everywhere. No, not like they used to be. They were snowdrifts of them. And so they were so heavy here, you think about bad reputation for a lake. It was really, who caused it? The humans that disrupted all of the habitat and all of the fish that used to feed off these guys. That's what caused it. And so the knockdown of the hitch and the streams and all the little fish were disappearing, and they were pulling up all of the near shore vegetation, and that's where these guys were, little fish were not doing so well because they didn't have their place to hide. The bass were nailing them. You got to have that stuff to keep the bass from eating all the little fish. Chironomids were everywhere. So we got to solve that problem. And so back in the 60s, they were putting in dichloro, diphenyl, dichloroethane, and so DDD. And so DDD was going into the water column really thick. And I've got a slide here for, So the producers, of course, were not too harmed by it. Yeah, knocked them down a little bit. And then the primary consumers were picking it up out of the producers, and then the secondary, they were picking it off of here, and they were picking it up off of here. And of course, you were losing that 10% each time. However, you were not losing the mercury that was methylated. It was going into the flesh. It wasn't going off as energy. You had to die for it to go off as energy. So I was picking it up at each level because it was taking so much of what these guys had to eat in order to get energy from this. So they were eating tons of this, and that had a lot of stuff in it. And then it was accumulating going on up the ladder. And so by the time you get to the bald eagle, you had 20 parts per million of DDT. You started out with 3 parts per million. 3 parts per, 20 parts per million, 3 parts per billion. What is that? Okay. You knock off a number there, you go back here, knock a number off. So what that is 20 million concentration. The concentration fold is 20 million. 2 million, sorry. I just knocked one off. I can't put it back. 2 million is the concentration. That's a hell of a concentration. That's why you have to be careful about what you put in the water column. So when I was sitting on the board, listening to testimony about don't worry about the herbicides we're putting in the water column because we tested and we can't find any. God, that made me feel good. I said, hey, I feel okay. So what was the result of all of this? We had the Grebe crash in the 1960s, which spawned the book that was DDT, by the way, which is the same as DDD. I should have mentioned that. But the Grebe crash, and that was Rachel Carson's book, which talks glowingly about the crisis problem we had here in Clear Lake. And so we were internationally famous for having misapplied and discovered the principle of bioconcentration. Was discovered here in Clear Lake. So it was a good thing. Now, I don't know if these two are going to make it because they're slightly out of step. All right, so the other principle that we learned when we were talking about climate is the El Niño effect, which pushes all the warm water over to the west. You get so much moisture that it comes up and gets picked up in the jet stream, and we have the atmospheric river storm, and that brings a drought reducing storm to California. About 40% of the droughts in California have been totally wiped out by these atmospheric river storms. So that principle happens. Unfortunately, we also get a lot of flooding. And when we get a lot of flooding, we can get a lot of ground starting to move again. And when the ground starts to move, that can have a negative consequence. This is a landslide. And this is a storm, let's see, back in, can't remember now, 2015, 16, something like that. We had when did we have the big flood event? 16, 17, something like that. And so they don't happen very often. But when they do happen, that's enough material to reload this lake. So it doesn't happen, they have to happen every year. So if you're going to storm-proof this lake, you're going to have to storm-proof it against big storms. Don't worry about the small ones. It's the big ones. That's really what they're missing. If you're going to do something with these streets, you better do something so that they will withstand those big storms and you don't have this kind of scenario. And building a road like that, which is in-sloped, and it's that steep without an outslope, rolling dip, or anything else, that basically every year turns into a torrent of mud that goes into the lake. And there's the other thing, another principle called sheet erosion. Real erosion is where it all concentrates. You can actually see, look at the evidence. You don't see the evidence from sheet erosion. That's where it comes off like a sheet. The sediment is picked up and comes off the landform like a sheet. You've got to have a marker that tells you it actually happened. And there's your marker on this one.
On that picture before, not to derail you too much, before this one.
Yeah.
So what can you do to get the water to go off?
Outslope. This is insloped. You just have to can it the other way, and then you put rolling dips in it like we do our road. Yeah. Now, everybody's been down Highway 29 right here? Okay, what has happened here is that Caltrans has all of this water that comes off the side. They collect it right here and it comes underneath the highway right there. Now Caltrans hasn't been there forever, and in fact that used to be a Indian Trail, and after that it was a wagon coach ride along here. So what happened was this was a gigantic vernal pool. One of the most beautiful things you ever see when you see one, because in the spring you get beautiful flower blooms that go through concentric circles. Absolutely amazing. One of the most amazing things about Lake County, this is what happened to it. A guy wanted to farm it back around the turn of the other century. And he wanted to farm it. And so what he did, this is a big lava flow right here, and he built a tunnel right here in order to drain it off. And then he would be able to have a dry field so he could farm. Wanted to put in hay or something for his horses back at the time. It all collapsed. So it sat there until 1930s. In the 1930s, a lot of heavy equipment started coming into the county. You're going to hear that as a theme. In 1930s, they moved all of that out of the way so this could drain and they could reclaim that land. So it drained off, but there was no nick point. You have to have a hard point to keep the soil back, like a dam. It's called a nick point. Well, there is none. It will just erode down. So it was going into Thurston Lake, which is an old collapsed volcanic vent. There's no bottom. There's no nick point. It's just going to keep cutting down, and that's what it's doing. So it cuts down, and also you have the water concentrating down at this part, so it's going to follow that line, and it's going to do that. So why did it make a circle? Well, look at how that circle is shaped. Back in the day, before all this happened, that was a racetrack. They used to race motorcycles around that thing, and everybody would come out and watch the motorcycles race around it. And so that was kind of cool. So now, of course, it's following that line of least resistance. It's going to connect someday. All of this is very fixable. We could actually get a vernal pool back. This is privately owned at this point. The other thing that happened on the lake, of course, we had the marshes around the lake, the very wetlands that I was talking about. They've been either scooped up or they've been made into a harbor or whatever. Up in the Middle Creek area, they put in levees in order to reclaim it for bean field production back in the 1930s. Did I get that right? 1930s, I think it happened, 1940s. And so with that happening, of course, that's when the heavy equipment came in, so they could do it. You can actually see where they scooped up right along this line to make the levee. They also scooped along this line to make the levee. All of that then becomes a farm. And of course, here's the Middle Creek Restoration Area right now. It's old farms. These were, at that time, was wild rice. And so if you have rice-a-roni, you have to have wild rice in there and all that other stuff. Well, it came from here. I mean, that was a pretty good market. And so from the bean fields turned into wild rice. And so this is now part of that reclamation area. So when that all gets done, we're going to have a better lake simply because the sediment will drop out before it gets to the lake. Right here is Clover Creek. It is not running anymore. It comes up and it connects with the town of Lakeport, but they put in the bypass that went over the top of Lakeport, Upper Lake. I'm sorry, I get it right. Goes over the top of Upper Lake and then comes down the side right here. And so Clover Creek now comes down that side along with Middle Creek and Scott Creek. They all go down that one side. And because you have all of that water run down one particular area, it's going to pick up that sediment, it's going to carry it with it. And it's going to carry it with it right into the lake. And that's what's been going on. So you have all this lake. This actually is a very large delta right out in here. But during this very low water period, you could see it. And I guarantee you, that is mucky. I walked out there to get a picture taken. You know, I'm going to walk out and show you how this really looks. And I started sinking, and I had boots on up to here. And when it went over the top of the boots and I was going to die, I said, somebody throw me a rope. And they were scrambling for a rope. I think I said it before then. And anyway, so somebody found an old limb and reached out, pushed it out, and I grabbed onto the limb and was able to crawl and swim. Both boots are still in the bottom of the lake. And so someday, somebody's going to go out there and find those boots and say, man, I wonder what kind of critter that was. That's a hell of a lot of material going into the lake. And that's one reason that we have the imbalance. And so when you finish Middle Creek, we're going to have a better balance. And so humans can cause lakes to fill in faster, and they can change nutrient levels, and ordinarily that will take a really long time. And of course, the bottom dropping out of ours even takes longer, but that's called cultural eutrophication, and it shortens those centuries down to decades. And there's some places where it really shortens it down. If you ever want to look up a place that's like ours, which is a tectonic lake in Hungary, called Lake Balaton, B-A-L-O-T-O-N. They basically got a handle on their eutrophication, did something because they were behind the Iron Curtain. The Iron Curtain dropped, everybody wanted to be a tourist. They had this stinky lake, and they wanted to have the tourists happy. So then the government actually got together, did something about it, they fixed the lake. So it's a great story.
In Turkey.
Now this is all of the information that the cores, anthropogenic stressors and changes in Clear Lake ecosystems as recorded in sediment cores. They went out and they drilled cores in the lake. They went down deep enough to where they could actually see just how much was coming in over time. And they could go back to the days of the Indians and so forth. Well, right here was the introduction, 5 I think it is, was the introduction of heavy equipment into Lake County. And what those cores found was that all of the problems of mercury and other problems that in the system, the increase in the siltation, all of it started in 1930 to the extent that it did. That's when the lake started going south. 1930s is when they built in fact, that was the building of the restoration. That was the start of the restoration of Middle Creek. So all of that restoration of the marsh started at that same time, and that's where they pushed tailings from the Sulphur Bank mine. In order to get more working space, they pushed those into the lake because they had big bulldozers to do it. Now, why is it that the upper arm might have more silt in it naturally than the other parts? Well, it's because all this blue is what empties into the upper arm. That's a lot of watershed compared to anything else. Now, all of this Oaks Arm drainage basin that goes into the Oaks Arm goes right in through here. That's the keys. So keep that in mind. The Clear Lake Oaks keys, that's where it comes in. And then everything down in here, some of it comes in through the city of Clear Lake. There's a place there, and there's another place down here where it comes in. And so that's everything that ends up into the lower arm, plus that comes in the lower arm. Thurston Basin has its own emptying, as you just saw, goes right into Lake Thurston, which is the volcanic vent. So right here, I'm right on time. So right here, we're going to take a 5-minute cookie break, and then after 5 minutes or so, I'm going to give you the where are we on Clear Lake. So we have the lake starting now. Where are we in this scenario? All this potential change since the 1930s, and really also in the 1960s with all the growth going on, and they didn't know how to keep the sediment out of the lake. And so it took a long time before they got different ordinances in place, the dredging ordinance, not the dredging, the grading ordinance, that sort of thing really made a difference, but nobody knows because nobody's monitored it. So what we need is some real numbers to know how well we're doing. That's where we are. We don't have the numbers. But so if you're sitting in the Clear Lake Oaks Keys, you can from time to time see the cyanobacteria floating by. And so it gets on the surface because, the reason you see it on the surface is because the cyanobacteria likes to be in a water column. It's competing for the light, so it floats up, it takes on a little gas bubble, floats to the surface, gets more and more light. There's less light penetration because there's more and more phytoplankton, more and more cyanobacteria, so it gets a little higher. Finally gets to the top, right on the surface where the sunlight kills it, and then it's floating. That's why you're seeing it like this. It's still in the water column though, by the way. And in fact, it blows down and gets into that east end and can concentrate it in the east end. Can you see all the green? Okay, and here's the Keys down here. Here's the Anderson Marsh down here, the city of Clear Lake right there. And of course, this is our famous mine right there. That's Borax Lake right here. So this is not your normal breezes that take it down that end of the lake. This is what's called a downslope breeze. It's adiabatic. We talked about that in the climatic stuff. So an adiabatic is a local breeze. At nights, you know, the lake, finally the pressure comes off and the cool air starts to flow down the hills because it's cooling off faster up the slope than it is around the lake because the lake's so warm. And by morning time, the pressure is equalized where it really comes down the slope and we can feel that breeze, and that's the downslope breeze. We also have the Konocti winds, where the high pressure during the day keeps the breezes, the pressure of the colder air off the coast from coming in. If you were in the delta, that'd be the delta breeze. We have the same scenario happening here locally, so they have named it the Konocti winds. And when they blow, there's very little lake stratification because the lake is basically mixing up very well. Right here you see all of the ripples are called Bernoulli waves, the little ripples on the water. And here's Bernoulli waves right here. Satellites picking up all that reflection. Right here it's very dark. What that is called atmospheric bounce. And so it's coming down, bouncing off the water, and then bouncing again like that. And that will actually move around in the lake, this bounce. Really fun to look at all the satellite pictures and see that bounce in it. These are called Langmuir lines. If you've ever looked at the lake where the wind is blowing 30 miles an hour and you've got these white streaks, has anybody seen that? Not white caps, but these streaks in the lake. That's called a Langmuir line. And that's, when you get the streaks, that's showing that you have high organics in the water column. So you can get these Langmuir lines and not see the streaks, and you won't even know they're there. When you see the streaks, that's when you actually have the high organics. So how does that work? A gentleman named Langmuir figured this out back in 1932, and basically he took an ocean trip, and out on the ocean he saw all the streaks. Did you get your picture? You want it? Okay. And so what it is the wind is blowing down these different areas, and when it blows, it gets down on the surface of the water. It basically is pushing the water aside, and the water's a little bit higher to the side, and so it creates a little more friction. And so here's the wind blowing along here, and there's a little more friction there, so it breaks the wind into these stripes as it blows over the surface. And so since it's blowing the water aside, pushing the water aside, and this one here is pushing the water that way, there's a natural downwelling. That downwelling happens just like this, and where there's a foam, it will actually get into a row, and that's where you see the lines. And so Langmuir lines happen on this lake all the time. When you see it, that means you have high organics. When you have high organics, that means you got too many organics out there. Something probably died. You probably have something that's recycling. And cyanobacteria blooms can happen when there's a lot of nitrogen available, a lot of phosphorus available, and it actually will dominate the surface to the point where it has a competitive advantage against the phytoplankton. So the phytoplankton are the things that use oxygen. Cyanobacteria are the things that really thrive when there's low oxygen or no oxygen. So they can basically get a competitive advantage. And in fact, depending on the species, this is your Lyngbia. I told you to look at the long line of Lyngbia. Okay, this is your Lyngbia. It dies, it floats to the surface. It has a lot of sulfur in it, and it stinks as a result. It has that garbage smell. And so you say, wow, it's really earthy out here. That's the sulfur that's coming off. And this was really earthy. And in fact, this is after they did the cleanup work. And so I just was able to catch one picture where it wasn't solid out there, because it was solid. This is the Keys area. So the Keys, basically all the cyanobacteria comes down and blows into the Keys. They weren't too happy about that because they said the county's not taking care of the lake, and therefore we're getting a lot of this cyanobacteria. So if it blows down and it dies and it goes to the bottom, then you have local phosphorus at the bottom end. Not much coming in from sediment, it comes in from the cyanobacteria, and it accumulates in the Keys and accumulates around Clear Lake Oaks. The Clear Lake Oaks and the Keys get it, and also the Clear Lake, the lower arm. So here is a little bit of ecology. So our great egrets like to get on these floating mats and peck at the little pollywogs that were in the water column. So we have, of course, another invasive species, which is the bullfrog. And so these guys are floating around in the top of the surface about this time of year. These guys are out there pecking at them. It's kind of fun to see this. Nature in action. We're not the only one this happens to. This is Lake Erie. Lake Erie, back in the 1960s and up through the 80s, were having a hell of a time. The fish were dying. They're losing their fishery. A great whitefish commercial fishery. It was stinking all the time. Well, they went and cleaned it up. They cleaned up everything. I want to show you a picture of how bad it was in a minute. But this is in 2011. It came back. What happened? Well, they got quagga mussels in the lake. So Angela De Palma from the county brought these. These are quagga mussels, and these are in pipes, and they grow them in Lake Mead, because they're in Lake Mead now. That was thanks to all the boaters that brought them from Lake Erie. But in any case, they will really proliferate. And they also had zebra mussels. So you have, and both of them are these very small mussels. This is them in an acrylic box. You can see just how small they are. That happens to be quagga mussels there. And what they do is they strain the water column and they extrude pseudofishes, is what they call it, full of phosphorus, because they have concentrated it in their bodies, and they've concentrated the phosphorus, the little bit that was there from the farmers' runoff. The farmers kept saying, we've already lowered our phosphorus as much as we can. There isn't much in the soil back there, because it was all covered with ice. It's all scraped off the top, not much phosphorus. They have to add phosphorus. It was running off during the storms, getting into the lake, so they reduced it by half. Everything was going fine. They got the mussels out there, concentrated the phosphorus. Now you get this kind of bloom. It was so much cyanobacteria, it shut down the water supply to large cities in Ohio. For several weeks, they all had to be drinking bottled water until this bloom moved off the coast. This is in 1969. The Cuyahoga River that empties into Lake Erie was actually burning at that time. So they did so much work that they kind of fireproofed it. But there was so much oil, byproduct and whatnot that was on the surface that the kids learned how to set the river on fire. And so they were doing that all the time. They set it on fire so much that it was not even making the newspapers. So that was the Cuyahoga, and they fixed all of that. Now they got a different kind of problem. So there's the guy causing the problem. That's the quagga mussel, and so it's pretty small. It's only as big as your thumb. And then here it is that when it gets onto a shopping cart. That's 1 million of them. That's what it looks like. And of course, now you can see why it plugs up those pipes like it did there. And here I am doing a study for the county down in Lake Mead, where they have water that they will bring out of Lake Mead, and they put it through these big troughs and whatnot. And we took Lake County water and some mud down there, and then we introduced the mussels into these Clear Lake water. So this is all Clear Lake water. We put a little turbidity in each one at different levels to see whether or not the information that was available about whether they would grow in Clear Lake was accurate, because it was very ambivalent. It said, no, it doesn't have enough calcium, doesn't have too much of that, not enough of that. So we took them down there and tried it. Not only do they grow, and all of the information was wrong, not only do they grow better in Clear Lake water than they do in Lake Mead water. And we got a whole spawn off, and all of the spawn worked just fine, thank you. And we kept all the temperatures the same there as they were up here. So that was that study, and we did a couple of more studies down there, but it was kind of fun. So some of the knowns, and I'm only going to take the top one rather than go through all of this. High phosphorus nitrogen loads drive cyanobacteria blooms in a naturally shallow, warm water, eutrophic lake. And all of the rest is just stuff I've already talked about. That's the key. And so it's sediment that comes in. And so we got a satellite photo that was shown at the board meeting. In fact, Denise is not here anymore, but she was a board member at the time. And this was shown, and she held it up and she said, Jesus, it's got to mean something. You know, hello, yes it does. And so the satellite imagery became very important at that time. We started really looking into it. And here's all of the different markers that we had. Borax Lake, here's the mine, and here is the Keys. It's coming in at that end of the lake, and it's really coming in through Middle Creek. So we asked the questions. Okay, it's coming into Middle Creek. And so we asked the questions such as, does most of the sediment come in through Middle Creek? Maybe it comes in somewhere else. What we really need, that might be an anomaly. We may have a storm only over one end of the lake. Happens all the time. One end of the lake gets a storm, the other end it doesn't. So we need a full basin, full county rainstorm in order to look at a satellite photo to see where it comes in. So we did get one 2012 winter, had a 7-day full basin, high intensity rainstorm where all of the stream systems were running and full. So in 7 days, everything is going to just unload. And this was during a drought, so that this was an atmospheric river storm that was breaking a drought. Perfect timing. And the other perfect thing about it was that we happened to have a clear day so we could get that satellite photo. And that satellite photo showed which streams were running sediment into the lake. And this was interpreted for phosphorus. Like I said, we can interpret them for phosphorus now. So that was interpreted for phosphorus, and it showed that everything's loaded up at the big end of the lake and it's full of phosphorus. And that's the turbidity that has phosphorus in it. Here's the Keys, not much coming out. Here was really a surprise. This is the marsh area, and we got a lot of phosphorus at the marsh coming off, and of course, the city of Clear Lake dumps a lot in as well. But that's where you have most of your phosphorus. And so there's Anderson Marsh, and here's the Clear Lake Keys. You can see how much development. We really expected it there. We didn't get it. You got a little stream that comes right down through here that would have emptied it in, so they don't get much. And so we had it interpreted for chlorophyll A. Now, chlorophyll A would be all of your primary producers. So I'll just skip to the bottom line. That's what that is. That includes cyanobacteria, and it includes phytoplankton. It includes all the vegetation and everything. And so there's your primary producers. They're lit up. The whole lake is full, and they're loving it in the wintertime. Lots of nitrogen from the storms. Now you can flip off the chlorophyll A and only have the phycocyanin on. Phycocyanin is the image for just cyanobacteria. So now cyanobacteria has been spurred to bloom during the wintertime. Now, if it's attached, if phosphorus is attached to the sediment, it's not available for cyanobacteria. It has to be processed in the mud first. So that means there's orthophosphorus in the runoff, which would be from other sources. That could be what's been generated up here in Tule Lake. This could be generated down here in the marsh, or it could be fertilizer. And about this time, we had a lot of illegal grows. It could be that because those guys were dumping their bags out, and they used 050, so, which is a lot of phosphorus. And so in any case, big white mounds of phosphorus. But in any case, we got this bloom. And the other thing, the interpretation is, we know that phosphorus drives cyanobacteria blooms, and they need nitrogen as well. But nitrogen really drives phytoplankton blooms, and that's what we want is phytoplankton blooms. The phosphorus is locked up in the sediment, so ortho-P, fertilizer, must be in runoff also. That's the question mark, needs to be tested. And then Anderson Marsh and Tule Lake may release phosphorus from the sediment. What it tells me is that when we do the restoration on Middle Creek, we better do it with an understanding of how, so we don't release phosphorus into a water column during the flood and get it into the lake. And that's going to take a little more science than I think they have right now. And then we have additional questions. I'm just going to skip this in order to save time and then go right to it. Here's what we did. Right after this, the storm, 2 months later, we got some more images. No more storms. That was the only rain we got. That 7 days was the only rain we got that year. And so in February, this is the next image that we picked, and there's still a little phosphorus in the water column. Tells me, because the turbidity is gone, it's all dropped out in 2 months. It tells me that, in fact, we did have some phosphorus that was released into the system. The other thing is, chlorophyll A is still blooming like crazy. So this is everybody else, all the primary producers, the phytoplankton is producing. So is there cyanobacteria left? In that bloom, there is not. There was not enough phosphorus for it to bloom and take over the whole picture. So this is a good time of year for the lake, sure enough. And we have to ask the next question. Part of the winter phosphorus was available to cause that bloom. Turbidity settled out. Anderson Marsh is still hot. Okay, let's see. Anderson Marsh was still hot. Yeah, we still had it going down here. So we think that's what came from the marsh. And so what happens during the summer? Well, unfortunately, there was politics being played at that time when the county was doing some good work. Not to go into it in detail, but if you ask me later, I will go into detail. In any case, we couldn't get the 2013 photographs interpreted. There were $500 for each one of these things. And there were people screaming the county was spending money on crap. And it wasn't. It was telling us how the lake worked, and there wasn't very many people on that radar. So anyway, the decision was made not to get any more. However, we happen to have already ordered 2011 series. And so we took the 2011 series and took one of the natural color images of 2011, and we said, here it is in May. So now all those storms are behind us. We know that there were storms in May, before May of 2011. So we did have rain coming in. And so we said, and look at this. Here's that atmospheric bounce. Isn't that slick? I just love that. In any case, so here's our image in May. Here's our total phosphorus left over in the water column in May. Here's the chlorophyll A. We don't have any bloom. This is beautiful. This is the lake you want. You know, if you're with a person that wants it to look like a bathtub, this is a beautiful time of the year. And so this is great. Now, I think that we need to have a little bit more green in it, but then I'm an ecologist. And so where's our cyanobacteria? It's not there either. None of it's there. This is great. That's May. What about July? There's July. So no more input. There's no more rainstorms. Where's it coming from? It explodes. It comes out of the sediment because of the anoxic conditions in the sediment, releasing phosphorus. Then all of a sudden you have too much phosphorus. And in fact, at this time, the nitrogen level in the free nitrogen that was in the water column was very low, very close to zero. But phosphorus was taken up. In fact, when they went to test for phosphorus, there was phosphorus, but not as much as you would expect. What it was all locked up in the cyanobacteria bloom. So here we are, chlorophyll A, the whole lake is lit up. And where's our cyanobacteria? It's everywhere. So it's not phytoplankton, it's cyanobacteria, and it's using up the phosphorus, and that's where it was locked up. So there we got it. It comes out of the sediment. You don't want sediment coming into this lake. And of course, it's always going to be a warm water lake. Where's the phosphorus distributed? It's coming up and being distributed by the the windstorms, pushing that. All of this is really, this red that actually shows up here from the phosphorus is dead cyanobacteria. That's what you're looking at. And so it's released into the water column and it shows up in the satellite photo. And so what's happening is you're getting the transport of phosphorus from that end coming out of the mud and coming over here, dying, and then going down into the mud here. And you don't have much sediment going down there, and yet you have high phosphorus loads. It's coming from the cyanobacteria. So that operating theory, all you need to do is go out and study it for that purpose to see if in fact that actually is happening, and that was not going on in any of the studies. But it was kind of clear from the satellites. I just would have liked to have had more data to back this up. I had some, and that's how I kind of deduced all this. But it's there, and if you were out there looking at cyanobacteria and you were to pick it from these different areas, you'd say, wow, it could be pretty toxic, particularly if it has a high phosphorus load behind it. And so here again is that cyanobacteria. This is just recently blowing down into the Oaks Arm, and then it kind of lays out along the shoreline. And of course, along that shoreline, you have your water pickup for the different water supplies, and they have to keep up with that, and it costs more money to do it. There's ways to do it. If they only have one intake right here for Clear Lake Oaks. If they were to have another intake down here in a little bit deeper water further out, then they could actually check the pH of the water as it comes in from either one of the two inputs and shift to the one with the less pH. Because cyanobacteria, when it starts to break down, goes bonkers on pH. So pH ordinarily is 7, neutral, slightly above 7 in the lake. Ordinarily it's a little bit to the caustic side, and it shoots up to 9. Wow. 9 plus. So it's a very high pH, and so you can actually tell when you get cyanobacteria in your water supply, and then of course if you can bypass it, then when it's in your treatment tanks, you're going to have less treatment chemicals, you're going to have less of an operation there. So that is pretty much how the lake works and how we want it to be because we're human, not necessarily because we're fitting a niche like the critters, but then I'm an ecologist, so I look at it differently, and that's the sunset on the lake. So there's your presentation. So, did I have any recommendations? Yes, I did. I've got lists of recommendations, and you know who's going to listen to me. And that's really the issue, is because the people that are looking at this stuff are not from here. The people that did the study was from somewhere else, and it always has to be a student that gets to, you know, you get the background and everything when they study it. They had 30 years worth of studies on this lake. And after 30 years of studies, they came out with a report in 1994. That was called the Clean Lakes Report. When I read that Clean Lakes Report, I said, you know enough to manage the lake. Why aren't you managing the lake? You never put a management tool in place to manage the lake. They even had a TMDL, a total maximum daily load limit put on by the Regional Water Quality Control Board. It said you can't put so much nutrients from the side of the slope into the lake, and yet nobody monitored how much was coming in, and they came up with a level of how much it should be, although they didn't know how the lake worked, so they didn't know whether that level was a good level. And they said they had modeling, but the modeling didn't have anything to do with, in fact, the lake as far as I'm concerned. How do you do it? What you have to do, do I have it in this one? Develop monitoring, teaching, meet with other agencies, investigate, work with, reduce sediment. You have to come up with a phosphorus loss rate in the lake compared to the input. And you can do that, you can quantify it. And the phosphorus loss rate has to be greater than the phosphorus input. So if you can figure out what the loss rate is, some of the water column goes out through Cache Creek. Some of the phosphorus gets locked up in heavy metals and is not used anymore. It's locked up in the sediment. And only the top 10 centimeters, 4 inches, is actually active to release phosphorus. So the more recent sediment that comes in is the one that's going to have the phosphorus to be released. So over time, as it gets locked up and that top 4 inches becomes less and less in phosphorus, you'll have less load coming into the lake. You want to know what that load rate is coming in, and you want to know what the lockup loss rate is going out. If you can determine that, you can determine how long it takes for this lake to clear up. The Regional Water Quality Control Board said, well, it's going to take 100 years. Where's your data? No data. And so they just did that so they didn't have to answer the question. And that's one of the problems I have with agencies. I worked with one for 30 years. And so my opinion is that we really need to get down to the science individually by lake and understand it so that we can actually come up with a formula for the lake and manage it. If you're going to manage this lake, you manage the watershed. If you manage the watershed and the inputs from the watershed in through the systems, you're going to have a really nice lake, and it's going to be more balanced and less cyanobacteria blooms. So that's mostly my opinion. And so here, I want to say, Angela brought these displays. I want you to come and look at it. And also, there's information here. Angela, do you want to say anything about it?
My name's Angela. I work for the county in water resources. I'm the invasive species coordinator. So if you have any problems and with your plants growing in front of your dock or shoreline, you call, you're probably going to talk to me. One thing I did want to point out is this is water hyacinth. This is an invasive plant. It's floating. You guys can see in here. This is a baby guy. A big one would be like a foot tall. I wouldn't be able to fit them in here. These are very detrimental. They're dealing with them in the delta. I have a picture I can send around, a little fact sheet. So you guys can see this is a boat. They're treating it, and this is like 2 feet tall, and it just will cover the surface and kill all the beneficial algae that the fish need, and just it'll be a big menace. And a lot of times it has a really pretty purple flower, and so people buy them for their water gardens. And guess what? They grow really fast because they're invasive species, and then people dump them out of their water gardens and think they go back in nature and put them in the lake. So we found a couple of these guys with the hydrilla folks from the state out like Glen Haven Oaks area. And so I'm going to pass this around if you guys want to look at it. And it's pretty secure. It should be okay. Drop it. But just look at that, and if you see any, you guys can call me. I'll put my card up here because we want to go and pull them out of the lake really fast before they grow and spread and then cause a lot of damage. Because if it grows too much, it just takes a lot more time and money to get rid of it. This one.
Why do you pull them out of the lake?
We literally just pull them out. They're free floating. They don't root. So we take trash bags and you pull them all up, and you can spend a whole afternoon and you're like, yeah, I got them. And then you see another clump over there. So you go over there and you pull it, and you see another clump.
Thank you.
Weeding on water.
These are beneficial plants. So we have the periphyton, which is the hair algae. You talked about this one, right? Yes, this is what you see on the bottom. Sometimes you see it in creeks. And then on the top is duckweed. Have you guys seen duckweed out there? It looks like little leaves. The ducks will play in it. It's really great for baby fish. These are both beneficial, and they actually compete with the cyanobacteria for nutrients. Sometimes they can get a nuisance if they grow too much. But that goes with this, and so you can see what these beneficial plants and the green algae, which is the beneficial algae, the fish eat, versus the cyanobacteria and the toxic algae that we don't want. So that's what goes with that one. I guess you can look at it or pass it around. The labels are on there, and they should stay in their designated spot. What's the other? Oh, we have pamphlets on cyanobacteria, one in Spanish, one in English. Take them, they're for you. Take some for your family. Last thing. This is called coontail. Have you guys seen this when you've been out? It floats. Sometimes it gets kind of brown at the surface. So recent research shows that this actually competes with cyanobacteria. It releases a little chemical that kills the cyanobacteria but doesn't harm other plants. And I just want to show you guys this. So as a manager of this lake, when we find research like that, we'll then incorporate it into our policy. So next year, when I'm looking at coontail in areas and where cyanobacteria is, I'll try to see if the presence of them are helping with our cyanobacteria problem. So that's that. So this is a beneficial, it floats around. And because it doesn't root, it won't get stuck as much in your propeller of your boat because it kind of just pushes away, right? Your boat goes along and it pushes away because it kind of free floats around. That's it. The last thing is we do have an event. If you like volunteering, we have the Coastal Cleanup Day, which is on September 21st, Saturday from 9 to 12. There's 7 locations around the lake. You don't have to stay for the whole 3 hours. You can come for an hour anytime. There's a site captain at each location, and it's a great way to help us start clearing up Clear Lake, picking up trash, we'll have water, gloves, bags, anything you need. So take one of these flyers. And I'll put my card up here. Is that good?
It's good.
Okay. Thank you.
Okay. Now, if we have any questions, just shoot them out. And I just want to leave it on a positive note. really Lake County's moving forward. All is becoming known. Once that Middle Creek project, which is, starting to move, we got money coming in, all the properties getting bought up. So everything I'm talking about is kind of a, here's where we are, but I'll tell you what, it's all positive going forward. I think we're gonna come out good. Smell like a rose if we all live long enough. But it's a big lake, and the neat thing about it is because it's warm water, it is processing things very fast. That's a good thing. That means the recovery rate's fast. If you got nutrients, it's going to crank it out pretty quick. As long as we can get those rates, we know what we're doing. Yeah.
Yes, so you just now brought up part of the question that we're moving forward on the Middle Creek restoration and flood control project. And I heard that we got some money possibly, but I always hear, it seems like you always have a caveat in your own personal opinion as to how much good that's going to do. You see this massive amounts of nutrient load coming in from Scotts Mill Creek and Clover Creek. So actually, what kind of timeline do you see? I mean, it's taken eons. I think they tried to do this for the last 40 years with this project, and nobody thought that this was very much of an economic driver, and this year it certainly wasn't after the fires and so forth. But what's your actual opinion of, number one, how soon that project can get done, and how soon after that will we see some verified?
Well, in my opinion, from what I've been watching the lake without data, right? Watching the lake and what data I could get, you can turn this lake around in as little as 4 years, as much as 10 years, or if that 100-year figure is accurate, I'd like to know what missing component we have, because there are some components that are missing. There are micronutrients that are limiters. It might be iron. And if it's iron, then actually we have a lot of iron. And if that iron then becomes a limiter for phosphorus and kind of attaches to it, then all the better. So I'm thinking 4 years, you're going to start seeing, if you get good years, you're going to start seeing better years going forward. It's the cycle years that get us. Things kind of build up, and then all of a sudden we get a big cyanobacteria bloom. That's poorly understood. It's because we didn't collect very good information along the time. This is the bad thing about science. It's kind of well, I wish that I'd gotten that also during that period of time, then I'll know more. But at the time, when you start collecting information, you got 30 years worth, you don't know as much as you thought because you didn't collect all the right stuff. So those, that Daphnia situation, where the chart where I showed how the threadfin shad ate the rotifers and all that stuff. Well, that data came from 30 years worth of collection, but they stopped collecting that data. And so basically we need more of that type of data. We need that in the monitoring going forward. Angela's department, her section, they need a steady source of income. You talk about government in a negative way, but actually it's government in these small units, these rural counties, that basically keep everything going. It's different than the news source, where you get the big government and you get big city populations, that sort of thing. And that's what you read about. But that's really what drives us here. It keeps us going in the right direction. They're underfunded. Everything seems to be underfunded. We could have had this project done a lot quicker if they'd been properly funded. Now, had they known about what they were doing when they made it a bean field over in Middle Creek, and that would have been a terrible decision. But at the time, it was an economic decision. Now it's an economic decision going back the other way. So I think we're going in the right track. Yes, ma'am. Environmental effects of what?
Of the off-gassing of the phosphorus?
Phosphorus does not off-gas at all. It stays in the lake. What off-gasses would be the mercury. So mercury can combine and go off as a gas, and it does. It doesn't very much out of our lake, but it does in a lot of, if you take it collectively, there's mercury all over the place. How do you measure the loss rate on the surface? It'll come back into the lake through rain runoff, and so it does get back into the lake. But from the standpoint of being concerned about mercury, there's 50% of the lakes in California have as much mercury in the fish as we do. And yet, there's kind of a general warning. We get a lot of bad press here, but Berryessa and Pillsbury both have just as much mercury in the fish, as do 50% of the other impoundments, because of the gold mining. The mercury they mined out of here and a lot of other mines went up to do the amalgamation of float fine amounts of gold up off to the surface.
have any environmental benefits?
No. No, mercury is ordinarily not found. It's very rare in the system. So mercury has been locked up over generations from wildlife and plants and whatnot taking it up, dying off, and then become coal. It becomes incorporated in the sediment, and it's not even recycled very much into volcanics because it isn't very much out there. But it gets concentrated where it does, in coal, that sort of thing. And so when you burn coal, you can get that mercury back up into the atmosphere. So that's one of the things that they finally realized was, wrong with coal, was, hey, we got more mercury than we realized. You test it, there's not much. You burn tons of it, and then there's a little bit more. And then when you burn tons and tons and tons, you got a lot more. And so then it starts to concentrate again. So mercury is a problem that was kind of discovered after you get all of the rest of your coal producing going, and you realize that today, in my view, one of the things that you really want to shut down is your coal burning. You have all of the things that you want to actually get away from is coal burning, because it has so many problems with mining and so many problems with mercury. Mercury can be, used in batteries. And if they go into the landfill, of course, they're going to be more locked up than they are if they're in the atmosphere. You really have to burn it to get it into a gas. Mercury actually in thermometers. We used to take mercury and put it on and it turned your pennies into dimes, That's not that much of a problem for you. You can handle mineral mercury in your system. It locks it up in sites of toxic action. And so these sites, they're instead of being in the toxic arena, it is sites where that toxic action is locked up. And so this happens in all life forms. They have these lockups, and then it sloughs out. Some of it will slough out in different ways. It'll get a polyp and then drop off, whatever. So mercury is not as much of a problem when it's mineralized form. When it's methylated, then it gets biomagnified. It gets actually in the flesh of the material that it uptakes. DDT gets taken up through the oil side. So any of the fat processes within a system will have your DDT concentrated. When we were looking for DDT, and actually DDD, in the system here, we found mercury. And holy cow, where did this come from? And this was back in the early 70s. And and of course the DDD was found in the 60s, and we wanted to see if it was still in the system anymore. And that's why we got some money, came over and did some research on the lake. And so basically the fat side of the process for DDD is, as it takes up in the metabolism, the birds could not, they couldn't compete with the way mercury interfered with the laydown of calcium. Calcium and mercury are very close in the system. So the bird eggs came out very thin. So the first job I had in Fish and Game at the Water Pollution Control Laboratory right out of school was to go down in Southern California and look for the DDT in the ocean water down there. And so we were sampling different things. I had another job sandwiched in between there, and then they asked me to go down and take over a lab in Southern California, and that's when we started all of the dives, and we put out what's called mussel watch. We would take mussels that you eat, those little mussels, out of the clean portion of the coastline. Yes, we do have clean portions. And we'd put them into nylon stockings, women's stockings. So you have a nice bag of mussels. We'd haul them down. They were cool inside a chest. We'd get them down there, put them in these things, and we would hang them out onto the wharf in Dominguez Bay out of Long Beach. And the reason we put it there was the only place left in the United States that was still producing DDT was Montrose Chemical right up the Dominguez Channel. And so we put those all along the coast, but we also put them there. And then we would dive on these, take them into the lab, puree them, run them through a gas chromatograph, and then along comes this big spike, and there's your DDT. And every place else, a little spike. When you got to the Dominguez Channel, it was just a big spike. Holy cow, it's still in the water column. So we wanted to go down and figure out why it was that we were having a problem. And the chemical plant let me onto their site. I said, oh, we're just operating with no problem at all. Go ahead and take your samples. They were right. It was pretty clean. but it was going off in a volatile form and settling out over the neighborhood, and then the runoff of the neighborhood was going back in the Dominguez Channel. And so they were told they had to scrub their system so that that didn't happen anymore. They decided it cost too much, so they moved to South America. And there's one thing that I found out about DDT. In the area right around the whole neighborhood, there wasn't one cat. And cats don't like it. They die. And so in South America, they have rat problems because they can't keep cats. And that's what they were telling me. He says, man, the flowers are great. Man, this is a great place for growing flowers. There's no insects. There's a lot of mice and rats, though. And the cats die early from cancer. So, and I says, oh, that's interesting notes. Keep telling me. And I all went into the report. So anyway, they moved. Anybody else? Yeah.
So the photographs of the satellite photographs and stuff were taken before this big change, let's just say, in the cannabis ordinances. And I know that when you see these trucks going by and these huge amounts of fertilizer, and they buy the best fertilizer in the world, and that is that something that, I mean, there's a lot of people doing it, and they're all doing it, and they're not necessarily big producers, but there's so many of them buying so much fertilizers. You go by these places and they're just bringing in by the pallet loads. Is that something that, I know they have TMDLs for all of the vineyards and all these people that are trying to do everything right. These people are not being controlled. They're doing it in a renegade fashion.
Yeah, the ones that are not doing it.
We're talking about people that just do 6 plants, but there could be like 10,000 of them doing 6 plants, 60,000 plants, and they're all buying tons of fertilizer because they think more is better. Do you think that being in a basin like we are here could have a significant influence on what's going on here?
Mm-hmm. Yeah, I saw plenty of evidence for it. So one of the nice things about working for the county, you can volunteer for anything, right? I was on the search and rescue, so I got chasing people in the backcountry trying to find them, and I was a tracker, so at night, I'd be tracking. One thing that I found was an awful lot of tripwires, and holy cow, what's going on here, and pathways back into the backcountry. And you're kind of concerned about the person you're looking for because they get in the wrong spot. But I found lots of illegal grows. They were all over the county, everywhere. And they were in backyards. They were everywhere. And they were using the 050 fertilizer, which is all phosphorus. So this stuff, they put it in bags in order to grow the plant. And then if they have to get out of Dodge, they can grab the whole thing and run, or they don't have to put it into the ground because they don't contain the root ball. So they have these root balls full of this fertilizer. Then when they're through for the year, they want to start over and get a fresh bag to really grow the plant. They broadcast it out over the ground, and then it goes right into the channels. And in fact, they think it's a good idea to put it down where it gets in the stream and wash away. They think that's good. So it's a matter of ignorance. And one of the things we started doing was letting them know that's really not so good. And you are causing a problem. Well, we're so far from the lake. Well, we got 480 square miles of watershed going to the lake. And you get these big storms, it all runs off, goes in there. So it's not rocket science, but if you don't know about it, then you can't launch your rocket. You just don't know what to do. And that's why I think all of this, part of my recommendations, is to make this into educational tools, get it into the high schools, get it into the farmers. I tell you, I talked to the growers not the growers of the cannabis, but the growers of the grapes, the vineyards. I had all of the owners in a room one day and talking about what we found, and their attitude was, we don't want that lake to be bad because people come up here and they will go through the tours of the wineries, and when the lake's bad, we don't see them. We'd love to have hotels, and we'd love to spend money up here on these things, but we can't unless that lake is good. And so we told them that they're part of the problem, but not from the phosphorus. They don't use phosphorus. Why don't they use phosphorus? The soil's already full of it. But what they did do is they had access roads going into the vineyards, and they did not put cover crops on top of that because they keep getting messed up. Well, you get sheet erosion off of those. And so for the first part of the year, you get a lot of sheet erosion that goes into the system and it goes right into the lake. How much that is quantified, I don't know. There's so much coming off the dirt roads. There's hundreds of miles of dirt roads that come in. Back in the day, they used to do all this gravel mining into streams in order to build the roads, have gravel for those. Well, those streams were loaded with fine silt that was in the interstitial space of the gravel that they were mining. That released that and went right into the lake. And then, of course, it head cut after that, releasing more and more and more as it went up the channel. And when it went up the channel, then the sides started to slough in. So gravel mining in Lake County, as far as I'm concerned, is 90% of your problem in the old days. Building the roads themselves, so you got runoff from that. Big problem, because water is concentrated on those roads, runs off the roads, gets into a side ditch, runs to a place where it can go into a culvert so it can go into the lake or wherever it goes. Spent years working with the foresters on roads, trying to figure out how to do ranch roads. It is well known how to do dirt roads. So I got the good information, sent it to our person that did Public Works, and was totally unaware of it, and they're starting to incorporate that into their work on how to do the profiles of these roads, but most of them are private. So the problem is that they're private roads. So if we could get that education program going, that'll really help out. And then if you get Middle Creek Marsh. If you restore Middle Creek Marsh and you don't restore the uplands and get the off-road vehicles so that they don't create a problem up there, you're going to fill in the marsh with sediment. And so all of that dynamic has to be in an integrated management plan for 480 square miles. That's what you need to do. And that's not too hard. It can be done. All of it's known. Everything I've told you is known. Everything that I've shown you is right in the books. All someone has to do is read it. Yes. We have 190,000 acres of burned wood. It is biochar that is on the ground, or some portion of it. It is not in short supply here. And so where you want to filter something in your garden, that's one thing, but 480 square miles of doing that, you're going to be upsetting the soil profile more than you'll be doing it any good. So from my standpoint, when I looked at it, it's a good thing to do where you have people that want to do it and put charcoal in the ground. I use charcoal all the time and bury it for plants and that sort of thing. But from the standpoint of this system, it's not going to help it because it's the sediment running off. And the sediment, when it runs off in the way that I showed you, it's not going through any filter. It needs to be held back, slowed down, and spread out so that it sinks into the ground. That's what needs to happen. So anything we do to actually cause water to concentrate like off roads, anytime we have water that concentrates because of a project, that's when you're going to have the problems for the lake. So while that's a good idea, it doesn't fit this particular solution. One of the ways that you clear out a pond, it's full of little critters in it, and it turns nice and green, is you throw a bale of hay in there. And it'll clean that baby right out. It's the same thing. You provide a surface, a substrate for bacteria to sit on, and then you're going to start to get that action. So that's an old farmer's trick, been around forever, but it'll clean a pond out right away. So that's the concept you're talking about. But if you don't do everything else that's overwhelming this system along with it, you can do all of these you want to do, and you're never going to catch up to the system. It's already got a tremendous amount of material already in it, and you've got to find out what that rate is of loss and input, and then do just the right things in the right place. And so biochar, while it sounds good, is not a panacea. And so any surface, just like the water going through your charcoal, that's just surfaces. I used to use charcoal all the time when I was working in the labs, and I thought, why is this like it is? And so I basically broke them down finer and finer and put them under slides and see what it's just surface. It's not any special thing. It is just surface area. And when you get a lot of surface area, you get the right bacteria, it'll process water. Yes, over here. Yeah. Mercury wasn't perfect for everybody, let me tell you. He didn't know they already had an early death rate anyway for back in those days. You didn't live as long as you do today. We deal with a lot of diseases just simply because everybody is getting a lot older, so we're getting pretty good at it. But back in the day, you know, the life expectancy was a lot less, except in those cultures that eat in a more pure way. the vegetation, that sort of thing. The Indian cultures, they live pretty old. They've had pretty older population in some respects. So it's all about what you take in. Mercury's not so good for your body. Yes, ma'am. Swimming in the water, you can get some swimmer's itch. There's lots of things. This is a natural pond. It's got a lot of critters in it. I mean, it'll scare you to look under a microscope. And so you just got to take the precautions you would here in any system like this. They've had problems over in some of the river systems that move slow, and they've had them in different lakes. And so we basically contaminate our lake all the time. And the lake itself also supports a lot of life forms. It's not that clean a place to do anything with. And so you got to use the normal procedures. Make sure that everybody uses a little clean out in their ears and get showers and all that sort of thing. Now, if you put your hand in the water and you get a rash, that's not unheard of with cyanobacteria. And especially where you get these foam areas, that's all concentrated. I've gotten skin rash from going out and sampling. That's not really what will cause the problem. It'll be different people or actually animals that are more susceptible because of a pancreatic disease problem. And so can be very toxic. I wouldn't have my dog drinking this water in the summertime.
On your face, your eyes, or your mouth,
Huh?
if you're just stuck in a boat or a kayak or something, it splashes on you, is that an issue?
No, that's not a big deal. I mean, you really got to be submerged in it and be in it for a while and splashing around it. And every time you see a horrific story in the press, it's possible no matter where you are, in all the lakes that's way, all of the streams, all the natural body systems. The only one that's safe for you is going to be your swimming pool that has a good chlorine test. So if you want to be in that, in that category, that's fine. But otherwise, as far as I'm concerned, well, anything but July and August is pretty safe lake. Yeah, the rest of the year, it's pretty safe lake. And so that's when all your cost for processing water is the lowest, and July and August is when it's the highest. That's what I look at. I was on a water board at the Clear Lake Oaks, and so I was over there in their face all the time saying, hey, what are we doing today, and how are you testing? And that was a lot of fun for me because that's, kind of my background. And then and then they showed me these pH spikes. I said, my God, that's the cyanobacteria. How come you guys don't do something about shutting it down when you get a pH spike? Then you'll have a water treatment that's lower. All you have to do is store it in your upper tanks, store it in your treatment pond or your treatment tank, shut it down, the raw water, shut out the raw water until you get a better pH value, then fill that all up real quick, and you'll always have clean water at a lower cost. Nobody thought about that. Now, I don't know if they did it, but that actually is something that I found out from the treatment that they were doing back in Lake Erie. So it's also possible here. Just the surface area of the hay, straw really is what it is. It's just the surface area, a lot of bacteria in there. They love that. It's a good home for them. There's other ways to filter the water. You can have the plants floating on a platform, and then the roots stick down into the water column and it processes it. That's another way that they've done it. It is problematic in different ways. But small ponds, these things work. Big lakes, not so much. This is a dynamic lake. And so you really have to look at your runoff, your input, and all of your rates of change and treat it like it's a dynamic lake and one of the most important types of lake in the world. And if we were to manage it that way, you're going to get a different result than we did get. However, this result that we're getting is actually one that a lot of critters like. Unfortunately, we put too many introduced species in here. That's one of the reasons that we get all the die-off and the rest of it. And if there was a fish that we could get rid of, it would be the carp. If there was a fish we could bring back, it would be the hitch. Oh, the hay bales? No, that's for a different kind of thinking. I use that a lot in my consulting work. Basically, that's for the water to come through, slow down the water, and then the siltation will settle out. Right. So that's to slow the water down. Yeah. It doesn't trap it so much as slow it down. Yeah. And I use it a lot for my work with endangered species, basically red-legged frogs and San Francisco garter snake. Well, what I found was if you lay that along the road where you're doing the work out here, you don't have to put the big fence up. You just lay the hay bales down. If they come up, they'll get underneath it and they'll hide. They won't get out on that open surface. And so at night, I'll come and I'll roll them back to see what I have. And I got all these garter snakes, and I count them up, release them back out, and then that works great for these construction sites. So there's all these little different things you got to kind of look to see what you're doing, and it'll tell you. The land will tell you how it works. So I'm going to take one last question. I think we're pretty close, aren't we? Let's see. Now, I thought when you said pallets, I thought you meant these stacks of pallets where they actually put water at the top and let them flow down over the pallets. The wineries use that often, and that really processes the water because the wood on the pallet contain a lot of surface area for bacteria, and when it drips through, it picks up a lot of oxygen out of the air.
Where do they use it?
Well, right down here at Shannon, he does that. You can, as you drive by, you can look up there.
Where are they catching the water from?
The water is from one of his wells, but it's so bad that he can't use it. So by doing this, clarifies the water, then he can use it. So anyway, thank you very much. Appreciate it.